Thank you for having me. So today I'm going to talk about a coloring problem on hypercubes. So in this talk, when I say a coloring, it always means the proper coloring. So let's start with some hypercube basics. So we write QD for d-dimensional hypercube. And the vertex set of QD is the set of binary strings of length d. And two vertices are adjacent if and only if they differ in exactly one coordinate. So there are some small examples for Q2 and Q3. And it's easy to see that QD is deregular and bipartite, and the bipartition is unique, E union O, where E means the set of even vertices, and O is the set of odd vertices. And an even vertex means it has the even number of ones in its coordinates. And the number of vertices is 2 to the d, and we're going to denote this quantity by big N. So in this talk, big N always means the number of vertices of the given graph. Okay. So we were interested in proper colorings on QD. So let's start with this question. What's the chromatic number of QD? 2. Yeah, because it's bipartite. So yeah, trivially, the chromatic number of QD is 2. So it's not an interesting question. Then let me change the question. So we define one notation, C sub QG. So that means the number of Q proper colorings of a graph G. So my first question is, what is C2 of QD, which means the number of 2 colorings of QD. So this is not a fair question because the answer is right there. So the answer is 2. And it's easy to see that. So once we fix the number of the color of 0, then all the color of the rest of vertices is fixed because we are using only 2 colors. So the color of 0 determines all the rest colors. So there are only 2 proper 2 colorings. Okay. Then let's move one step further. What is C3 of QD, which means what's the number of 3 colorings of QD? And it turned out it was not an easy question. So the exact formula for C3 QD is not known yet, and I doubt we can find it. But the asymptotic formula is proved by Gavin in 2003. So he proved that C3 QD is asymptotic to 6 times E times 2 to the n over 2. And later, Engberts and Gavin conjectured C4 of QD is asymptotic to 6 times E times 2 to the n. And Tan and I proved this result recently. So we are going to talk about this result today. So at this point, people usually ask 2 questions. The first question is, why E? So this E is what you know, the famous rational number. And let me remind you that we are counting the number of colorings. So we are counting something and we see this famous irrational number. So how come we have an irrational number for the answer of this question?
You have a 1 plus 1 over n.
1 plus 1 over n.
Something like that.
Okay, we'll see this soon. And yeah, the second question is, okay, so we talked about the number of 3 colorings and the number of 4 colorings. Then what will happen if we have more than 5 colors? So actually the conjecture for Q bigger than 5 is given by Engberts and Gavin, but the formula is not as nice as 3 colorings or 4 colorings. So actually, those 2 theorems are quite pretty, but when Q is bigger than 5, then the formula is not as pretty as the given ones. Okay? So are there any questions?
So just out of curiosity, why is C2 QD 2 instead of 1?
C2.
So why are we not just counting
because
instead of actual assignments of colors?
I'm sorry?
So why are we not just counting partitions instead of assignments of colors?
Okay, so the number of colorings.
Yeah, but the bipartition is the same. So it's the same partition.
Yeah.
You cover 0 red, and then the others are given, or you cover 0 blue.
No, I know what you're saying. No,
Yeah.
well, I mean, are they the same partition?
I don't know, maybe people just wanted to distinguish the colors, and actually we can derive the answer to your question from this formula easily, right?
Right, well, I mean, it makes your formula simpler, right? Like the 6 goes away in theory.
Oh, I don't know, maybe. So the question is number of two colorings, and if we do not distinguish those colors, then maybe we have to add something to the question. I don't know, so make so.
What do you do for C4?
Even for 3 colors, you cannot divide by 3 because some colors don't have a. Oh, I don't know.
I mean, if you have a partition into 3
non-empty sets?
or 3 non-intersecting independent sets, you can color that with the colors 1, 2, 3.
Yeah.
And how many rows? We're always looking at partitions into 3. Oh, I guess 3 non-trivial.
Oh, what do you mean by non-trivial?
When they use the chromatic polynomial, they're counting colors this way.
Yeah, I think so.
Yeah.
So I figured that.
Okay. So I think they are all equivalent questions. Okay, so any other questions? Then, okay, so let's answer those questions. So the first question is why E? Let me start from there. And, okay, so I'm going to give you some heuristic. Oh, so our claim is that C4QD is asymptotic to 6 times E times 2 to the n. And what I'm going to do is to show you some heuristic. And this will give us some a lower bound too. So let's do this together. And when we consider 4 colorings, then the simplest coloring that we can think of is, I think it's this. So we have this bipartite graph, and let's say this is E and this is O. Then the size of each bipartition is n over 2. And the simplest 4 coloring might be this. We assign color 1, 2 for the odd vertices, and 3, 4 to the all even vertices. And then the number of such colorings is, so in this case, every vertex has 2 choices. So the number of such colorings is 2 to the n, right? Okay, then let's consider another simple case, namely, how about we assign 1 to all the odd vertices and 2, 3, 4 for all the even vertices. Then what's the number of such colorings? Yeah, so we have 3 to the n over 2. And this is radical 3 to the n. So it turned out this is negligible. So this means we do not have to count such colorings because this term is here. Okay, so that means to get 6 times E, we have to think about another variation of this simplest case. And that is, so we have O and E, and a variation is this. Again, we assign 1, 2 for all the odd vertices, and 3, 4 to all the even vertices, but 1 vertex. And we call this a bad vertex. So this bad vertex do not follow this mainstream. So we assign color 1 or 2 to this vertex. Then how many such colorings are there? For example, if we assign 1 to this vertex, then what happens to all the neighborhood vertices? Yeah, they're just fixed because when we assign 1, then they have to be 2. So they all lose choices. So the number of such colorings is 2 to the n minus d, because we are talking about Q sub d, right? Okay, but this is not the end because V can be any even vertices. So we have to consider the choice of V. And because V can be any even vertices, the choice of V is n over 2, which is 2 to the d minus 1. Right? So let me call this term A and this term B. then the number of such configurations is A times D, which is we have 2 to the n, 2 to the minus D, 2 to the D, so they cancel out, and we have 2 to the n times a half. So we have this another main term, which will contribute to this term, right? And we continue. So generally, consider so still the mainstream is 1, 2, and 3, 4. And in this case, we have K bad vertices and L bad even vertices. So K bad odd vertices and L bad even vertices. And we assume further that all the neighborhood of each bad vertex is disjoint. So this is a quite strong restriction, and we are counting the number of such colorings. Then, A term is, so the number of such coloring is 2 to the n minus, because all the neighborhood vertices lose choices, so 2 to the n minus K times D minus L times D. Then how about B? So the choice of bad vertices is, first, for these vertices, the choice of those vertices is, so here I use this notation, which means it's not the exact value, but it's n over 2 choose K, times the choice for these even bad vertices is approximately n over 2 choose L. And this is again approximately. This one is n over 2 to the K over K factorial times n over 2 to the L over L factorial. So remember, this one is 2 to the D minus 1, and this one is 2 to the D minus 1. So A times B will give us, so there 2 to the negative KD cancel out, 2 to the L times D cancels out, so what's remaining is 2 to the N times 2 to the negative K over K factorial times 2 to the negative L over L factorial. Right? Everybody happy? Okay, now let's sum this up. For all K and L, because we are counting all the cases, so it will give us 2 to the n times 2 to the negative K over K factorial, summation squared, because we have the same K and L. Then what's this? It looks very familiar, especially for freshmen. So summation x to the K over K factorial. What's this? E to the x. So this one is gonna be e to the half, right, Professor You look surprised. So we have 2 to the n times. So finally, tada, we have this famous or notorious famous number. Okay, so we got e times 2 to the n, but over there we have 6 times e to the 2 to the n, e times 2 to the n. Then why do we have 6?
Oh, the 6 was when you chose already? And the 4 choose 2?
Yes, 6 is 4 choose 2. Because we fixed the mainstream, but there are 6 mainstreams, so we have to multiply 6 to get the number of 4 colorings. Okay, so this is a heuristic, and do you understand why it gives us a lower bound? Because we only counted very pretty colorings, right? So here, as I said, this is a quite strong restriction. So we assume that all the neighborhood is disjoint, and also all the neighborhood of a bad vertex does not contain any bad vertices. So this is very strong. And what this claim says is that this lower bound is all. So all the other not so spatial colorings are negligible. So what we did in our paper is we considered all the other bad cases and summed them up and showed that the sum is still little o of 2 to the n. Does this make sense?
So is this how they came up with the conjecture?
Yes, yes, exactly. So they conjectured that all the not so spatial colorings are negligible. Okay, so.
Can you touch your laptop?
Oh yeah, touch. Oh, page up.
Yeah.
Okay. Okay, so then I have one thing to tell you. Conjecture for Q bigger than 5. So let's talk about that case. What happens if Q is bigger than 5? So in this case, let me just show you an example. And let's talk about the case that Q equals 6. Because when Q equals 5, the situation is not so symmetric, so it's easier to talk about Q equals 6. So in this case, let's copy what we did for 4 colorings. So in this case, the mainstream is gonna be 1, 2, 3, and 4, 5, 6. Then what's the number of such colorings?
3 to the 3.
Yeah, 3 to the n. So we might expect that this one will be our main term, but it's too good to be true. So if we have one bad vertex here, then what happens to its neighborhood? It does not lose all the choices, but it has 2 choices, right? So the A term is gonna be 3 to the n minus n times minus d times 2 to the d, right? All the neighborhood vertices have 2 choices. Then what's B? B is still n over 2, which is 2 to the d minus 1. So A times B will give us 3 to the n times 4 over 3 to the d times 1/2, but we don't care. So do you see the difference? In this case, that one. That case only gives us some small amount of the main term. But in this case, we have this, which tends to the infinity as d goes to infinity. So here, this pretty coloring is not the main term anymore. So roughly speaking, we say that almost all colorings contain some flaws. So we have to consider all the other bad cases and add them up, and we don't know how to do this. So this is why it's hard to think about when Q is bigger than 5. Okay?
I would kind of think of it the other way. If you did a random coloring on there,
Random coloring?
a bunch of those vertices, that V won't see, a bunch of them won't see all 3 colors in their neighborhood. So it's got some,
So you mean...
it has a chance to be color 1, 2, or 3, right? A bunch of those on the bottom have a chance to be 1, 2, or 3 because they don't see all 3 colors in their
So
neighborhood. So
yeah.
That's why they have
That makes sense.
more choices.
That makes sense. Okay, any other comments?
그래서 보드랑 이론으로 클래스를 2개로 나눠서 컬러스를 저렇게 줬는데 만약에 보드 이론을 떠나서 3파트 타입으로 줘서 각각의 파트 타입 셋에 컬러를 2개씩 준다면
3-part 타이트가 가능한가요?
그러니까 만약에 그렇게 클래스를 좀 쪼갤 수 있다면요? 파트 타입에 한쪽으로 그냥 2개로 나누는
오,
저 더 작은 게 나오고.
네, 작은 거.
yeah, so I don't think. Okay, good question. Any other questions? Okay, then so I answered those 2 questions, and let me skip the history because I want to put. Oh, why? Yeah, because I want to put more focus on our methods, which is entropy. Okay, so this is the theorem that we proved, and the proof uses combination of isoperimetry and entropy. And isoperimetry was used for dealing with situation B, and entropy was used for A. And in this talk, we're going to focus on entropy and sketch a proof of this weaker proposition. So to show you how we use entropy to count the number of 4 colorings. So this is a weaker proposition which says that if G is the regular and vertex and bipartite, then C4G is bounded by this quantity. And please compare those two quantities. So in our theorem, it has 6 times e times 2 to the n, and here we have 2 to the n times something tends to infinity. So this is much weaker bound, which is natural because we didn't use anything about hypercube in this proposition. So the sophisticated structure of hypercubes give that tight bound. Okay? Okay, then let's prove this proposition. And to do that, let me introduce some entropy basics. So yeah, I'm doing probabilistic methods, so I consider it always starts from x, which is discrete random variable. So x is a discrete random variable, and p of x is defined by probability of x equals x. And we define binary entropy of x by h of x equals that notation. And log always means log base 2 because the notion of entropy comes from the information theory. So that has to do with computer science. So binary is much more natural than anything else. Okay, so that function looks weird when you see it for the first time, but it turned out h of x is it behaved very well to represent the amount of information or randomness in the random variable x. So let me show you an example. So for example, if we choose x in R, let's say it has R possibilities, and this is uniform at random. And just for example, I want to calculate what is h of x for this x. So h of x is, as I said, summation of px times log 1 over px. And what is p of x in this case? It's uniform from R set. Yeah, so it's 1 over R. So we have summation 1 over R times log R. So because we are adding for R terms, so it's R times 1 over R times log R. So it gives log the cardinality of R. So it means, for example, if we have a fair coin, then in that case, so if x is a fair coin, then in this case, h of x is going to be 1, right? So this means when we throw a fair coin, then it has 2 possibilities, head or tail. Then how many bits do we need to encode this information? 1, because it has 2 possibilities. So this represents the amount of information in this random variable. On the other hand, then how about what if x is a fair die? In this case, we'll have h of x is log of 6. So, right? So, right? Right? Okay, so in this case, so intuitively, when we have a coin and a die, which one has more randomness? When we throw a coin, it only has 2 possibilities, but when we throw a die, it has 6 possibilities. So we want to say that a die has more randomness or more information than a coin. So this represents that property. On the other hand, what if x is a biased coin? So in this case, so this is a general property. Generally, h of x is at most log of range of x, and the equality holds if and only if x is uniform. That means if x is a biased coin, in this case, h of x is smaller than 1. And this is also natural because once we have a biased coin, then so for example, we have a coin with like, so its head, it shows head with 99% of possibilities, and it shows tail for 1% of possibilities. So in this case, the randomness contained in this coin is not as big as a fair coin, right? Because it's more predictable. So in that case, we want to say that this biased coin has less randomness than a fair coin. So this property represents that, the situation. Does this make sense? Yeah, so for the further argument, I want to point out h of x behaves like the amount of information or randomness in x. And we'll continue. Okay, so then how we use this property this property of entropy for a counting problem. So here, what we want to count is the number of 4 colorings of G. So let's call that curly F. And so this is a deterministic situation. We just want to count the number of 4 colorings. And to make it random, we do this. Choose a coloring in F uniformly at random. So at this moment, F is not a fixed coloring anymore. It is a random variable. So because it's a random variable, we can think about h of F, the entropy of F, and by that property on the top. So that says that if X is uniform, then h of X is exactly the same as log of range of X. So using that property, we have h of F is exactly the same as log of the cardinality of F. So if we can bound h of F, then that's the same as we can bound log of the cardinality of F. So by using this property, we'll bound the size of the number of 4 colorings. Does this make sense? Okay. Okay, so let me summarize. We want to show that h of F is at most that quantity. And let me give you some more notations. F sub u is the value of F at u. So this means the color of the given vertex. And F sub big U is the restriction of F to U. So which means the color assignment of the given set U. Okay? And the main point is that h of F is equal to that weird notation. Let me explain it. So I wrote h of F is h of F sub E plus h of F sub O given a sub E. And this notation is called conditional entropy. So the definition of this notation is the expectation of h of this. So this is conditional probability. So x, when we look at x, this is a random variable. And when we add this condition, it gives us another new random variable, right? Mm-hmm. Right? So when you put a condition, then it generates another new random variable. So this is simply the entropy of this new random variable. And this is defined by the expectation of the entropy for all the possible y's. So this is only the definition, but we are not going to use this. What we are going to use is this interpretation. So we look at h of x bar y as the average amount of information or randomness in x after we look at y. So it makes sense, right? So we look at y first, and then this is the randomness remaining in x after we see y. So in that sense, this property makes sense, makes very much sense. So this is another random variable. Two random variables can be one variable, right? Because when we throw a die and a coin, then a die and a coin can be one random variable with the joint distribution. So the entropy in xy is the same as, first we look at y. So this is the randomness in the random variable y, and this is the randomness in x remaining after we see y. Does this make sense? So I want to point out that this is a rigorous property, not like just intuitive expression. So I can prove this using some like Jensen's inequality and some properties of probability, but let me skip this because time is limited. But I want to point out that this makes sense, this intuitively makes sense, and we're going to use the interpretation to prove this, or to show you the proof, okay? So what this means is that this is the information about the color of all the vertices, right? And this is the information about the even vertices, and this is the information about odd vertices after seeing even vertices. So we only used this part. And what this says is that whenever we have some random variable, then we can choose what to open first. So in this case, we opened even vertices first, and then opened odd vertices, given the color of even vertices. So this is a clever way to calculate the colors, because if we don't look at even vertices, then each odd vertices has four possibilities. So this is too much. However, if we know what's the color assignment of even vertices, then it gives some restrictions on the color of odd vertices. So it's a clever way to open the information. And one more thing that I want to point out is it's kind of like trade-off, which means, okay, so what do we want to do? What we want to do is to bound h of f using that quantity. So that's what we want. So what we want to do is to find an optimal bound for this expression. So we always want to minimize the upper bound of this quantity. So for that, we cleverly chose what to see first and what to see second. And if we want to minimize this. And if we look at too much information for this, okay, so if we look at too small information for the first term, then that increases the second term. Because if you look at too small information, then that means in this term, we have small amount of prior information. So that means we have to pay a lot to see the rest information. On the other hand, if we decrease this part, then that means we opened a lot of information for this part. So it increases this part. So this is why I say that we have to cleverly choose what to see first and what to see second. And so what we want to do is to balance those two values to get an optimal bound. Does this make sense? Any other questions? Any questions? Okay. Then what's left is to analyze term by term. So first, what happens to this expression? Okay, so this is the information of even vertices. And again, we use some smartness for this term. So what we do is, rather than opening all the even vertices at once, we open it by neighborhood-wise. So this is the even vertices, but we do not open it at once. Instead, we open it neighborhood-wise for all the odd vertices. However, when we do this, there are some overlaps. How many is that? So in this expression, for any fixed vertex, this term is contained d times. Yes, that's why we have to divide it by d. And this is not equality. We lose something when we do this. So this is inequality. And I'm not going to justify this inequality. This is called Schur's lemma. Which can be rigorously proved, but we are not going to do this. Okay, and then we use another smartness to bound this term. So here we want to bound h of f sub nv. So this is the color assignment of n of v. But this is too much information to open it at once. So what we do is, instead of opening this information, we see this first. What's this? So this is just image of N of V. So this means this is the set of colors which is used for N of V. The color.
The difference between the left and the right?
Oh, so this is the color assignment. So it contains the information about the color assignment of each vertex. So V1 has which color, but this is only the set of colors.
Oh, okay. I gotcha.
And then using this formula, this can be expanded H of F sub N V bar F N V. So I just used this. So what I did is, this is too much information to open at once. So instead, I opened this information first and calculated the remaining information in this term. Then what's the benefit of this?
So you're going to figure out how many colors are used on the neighborhood. And
Yeah.
it's easy to figure out the second term or something?
Yeah, exactly.
Okay.
Exactly. So for example, if we luckily have only one color in this set, then that means N of V is monochromatic. So that means the randomness in this term is 0. Because the given set is monochromatic, so we don't have to pay anything for the color assignment of this set. And because this term is the average amount, so that monochromaticity will decrease, will give some small bound, some like good bound for this term. Does this make sense? So what we always do is to cleverly divide the information to pay less, or why pay more? Okay, so this is the first term, and let's go to the second term. The second term is too high. Okay, so for this, again, we separate the information. So first, instead of look at all the odd vertices at once, we divide it like H of F sub V given this for the sum of all the odd vertices. So we just separate the information vertex by vertex, and we'll lose something by doing this, but that's not so much. So we can do this. And again, this is too much. We don't need this much information, because here we are curious about the color of V. And to determine the color of V, we don't have to look at all the even vertices. What do we need? Neighborhood. Yeah, so instead of look at this too much for information, we can just look at this. And in here, the inequality is this way, because intuitively, we have some smaller prior information, so the randomness is increased.
Actually, shouldn't it be equality that one?
Equality?
You didn't lose any information, right?
I cannot say that that's exactly the same, yeah, because we have to consider, like, I don't know. So I think, yeah, but to be safe, to be safe. Okay, and again, we don't need this much information, because to see the color of V, we don't have to see the color assignment of the neighborhood. What we need is just the set of colors which is used for N of V. So again, this is enough. And again, because we have smaller prior information, so the entropy increases. Okay, so let's move to final. So that H of F is, when we use the first inequality and the second inequality, we have, this is at most summation V in O 1 over D H F NV plus 1 over D H F NV click bar F, and it doesn't work. Oh, it works. It's just slow, like me, plus H of FV given HF what V. So we have this. Okay? Everybody happy? So I just combined the first inequality and the second inequality. So we get this. So this is the last phase. Here, we have this. And this is a very small amount of information because it's only the set of colors which does not have many possibilities, right? So it's just a subset of 4 colors. And as I said, it doesn't have. So as I said, H of X is at most log of range of X. So because this one only has big O of 1 possibilities, so this term is big O of 1 over D. Right? And this is where that big O of 1 over D term comes from. And for the second term, we look at this. And I'm going to skip the full calculation, but what I want to say is that I want to remind you the trade-off thing. So here, this is the information or randomness about randomness in the neighborhood. And this is the amount of randomness in V itself. And if we have more possibilities for the neighborhood, then that means the small amount of randomness in V. Think about this. We have V and its neighborhood. And if this is monochromatic, then that means the randomness in the neighborhood is small. But if it's monochromatic, then V has more possibilities. On the other hand, if this has like 3 colors, then that means it has more randomness because it has more choices. But that reduces the choice for V. So those 2 terms are like, if this one is big, then this one is small. If this one is big, and then this one is small. So it's like this relation. So we could show that this term is at most 2. And the intuition is this, like this, seesaw. So we have, how many vertices do we have for the odd partition? N over 2. So this one is N over 2, big O of 1 over D, plus 2. So eventually we have N times 1 plus big O of 1 over D. Please don't ask me why it's not 2D. Okay, so this is the end of the proof. Any questions?
Oh, that's it?
Yeah, that's it.